Okay, this lesson covers how to prove inverses using composition. So I know you've seen this before. This is coming from the first semester, and there was a theorem. And a theorem is just a statement that you can prove making logical arguments, especially with mathematical or math concepts. Okay, so the theorem says the following. It says that any function f of x and a function g of x are inverses. So those two functions are inverses if the following compositions are true. So if and only if, and this word, I don't know if you guys remember this, but in math, you saw this in geometry. This means if and only if, which means this is a biconditional. If and only if, when we do the composition of f of g of x, and that gives us x, and if we do the other composition, meaning g of f of x, and that also gives us x, then it says that these two functions are inverses if this happens. So when you do this composition, you only end up with x, and when you do this composition, you only end up with x. Then you can conclude that the functions are inverses. So I'm going to give you the first example using that theorem. So what I'm going to do is, on this column here, I'm going to do first the composition of f of g of x, okay? And on this one, if this is true, then I'm going to do the other one, which is g composed of f of x is equal to. So let's do this one first. So what I'm going to do is I'm going to keep f outside of the parentheses. So this is the function f, and then instead of g of x, I'm going to look at what g of x is equal to. G of x is equal to this, so I'm just going to copy the square root of x over 7. So once we copy g of x in here, what g of x is equal to, then pay attention to what the function f is going to do to this. First, it's going to multiply by 7, and then it's going to take the square. So I'm going to do that next. So here comes that 7 from here, and then open parentheses. Inside of the parentheses, you have x, the square root of x over 7. But then when you close the parentheses, you must take the square. Okay, so then once you've done this, when you take the square, when you take the square of the square root, that's going to cancel the square root. So then we have 7 times x over 7. Notice that we have 7 being multiplied by x over 7. So those 7s simplify or reduce to 1. So then all that's left is x, which means the composition of the function f of x with g of x is equal to x. So then this condition is met. Okay, so again, this is called a biconditional because they both have to be true. Let's go on to the next one. So now notice that g is outside, so I'm going to keep the function g outside. Inside of the parentheses, I'm going to replace this with what f of x is equal to, and f of x is equal to 7x squared. So then this is 7x squared, and now pay attention to what the function g is going to do to this. So then this is equal to, g is going to take the square root and then divide by 7, which means instead of that x, I'm going to copy 7x squared. So inside of the square root, we have 7x squared over 7. And as you can see, there's a 7 in the numerator, 7 in the denominator, so that means the 7's reduce to 1. So then what's left is the square root of x squared. But when you take the square root of x squared, that gives you only x. So then this composition also gives you only x. So then once you've proven this, then we can make the following statement. We can say that f and g are inverses. How do we know? We just proved it. We did the two proofs, or this proof, and we got x on this one and x on this one, so that meets the theorem's conditions. So we're done with this example. Let's go then to example number 2. So for example number 2, I'm going to do again the same. I'm going to do this composition, f of g of x equals, and the other composition, g will be outside and f inside of the parentheses. Okay, Now, if this gives me something other than x, then I don't have to do this one. I can just conclude right away because it's a biconditional that the two functions are not inverses of each other. So then keep the function f outside. Inside g of x, which is the square root of x plus 1 over 2. Okay, so then from here, I'm going to look at what the function f is going to do to this. So first it's going to multiply by 2, and then it's going to take the square and then subtract 1. So let's see. So there is that 2 from here. And then open parentheses. So this is the square root of x plus 1 over 2. Close the parentheses, then take the square and subtract 1. Then from here, when you take the square of the square root, this is what we end up with. So this is 2 times x plus 1 over 2 minus 1. Then this 2 and that 2 simplify because it becomes 1, right? So then all that's left is the x plus 1, but we have this minus 1 waiting. So as you can see, plus 1 minus 1, the 1's cancel, and all that's left is x. So far, this says that f and g are inverses, but we still need to do the other proof. So check on this one. So let me do the other proof now. So g is outside. Inside is f of x. F of x is 2x squared minus 1. Okay, now pay attention to what g is going to do to this. It's going to take the square, take the square root, add 1, and divide by 2. So then this is equal to, inside of the radical or square root, we have 2x squared minus 1, but then it's going to add 1, so plus 1 over 2. So minus 1 plus 1 cancel. So then what we have left is the square root of 2x squared over 2. Now these two reduce to 1, so then this is equal to the square root of x squared. When you take the square root of x squared, that gives you x, which means this composition also gave us that this composition is equal to x. So we're done. Then all we have to say is that f and g are inverses, okay? Because they meet the theorem's condition. That is, when you compose f of g of x, that gives you x, and when you compose g of f of x, that also gives you x. That's our conclusion. For the last two examples, what we have to do is, this says for each function, state domain and range. So domain and range of the given function. So this is the given function, and its inverse using interval notation. Okay, so what we know about domain and range of inverse functions is that the domain and the range switch. Okay, for switches for inverses. So once we know the domain and the range of f of x, then all we have to do is switch domain and range for the inverse. All right. So I don't know if you can see the domain and range from the function itself, and if you don't, then sketch yourself a graph, which is what I'm going to do next. So this, let's say this is where x is negative 14, because that plus 14 inside of the radical means it's going to go to the left 14. And minus 5, that's the y value. So let's say this is minus 5 somewhere here. So then this is where the graph starts, okay, at negative 14, negative 5. From here, this is the square root graph, so then it looks like this. So once you see the graph or get a picture of the graph, then you can see domain and range. So if you can't see it here, then sketch yourself a graph and then see if you can see the domain and range from the graph. So by looking at the graph, we see that the farthest to the left this graph goes is negative 14. So don't forget domain, you go left to right. So negative 14 inclusive or including negative 14, but then as it goes to the right, it just keeps going to positive infinity. Okay, so that's a domain. The range, this goes from negative 5 to infinity. So it does have a bottom, and the bottom is negative 5, but then it goes to positive infinity as it goes up. Okay, And once you have the domain and the range of f of x, then all you have to do is switch them to get domain and range of the inverse. So the inverse domain will be the range of f of x. So then this is from -2 to positive infinity. And the range is the domain of f of x. So then this goes from -14 all the way to positive infinity. Yes, yeah, you're correct. Domain is, I don't know why I said -2. Thank you. Change this to -5.
That's 10 points on her last.
Yes, sir. Yes, she gets 10 points. So that also changes this. Man, you guys are awesome. Thank you for correcting me.
You're welcome.
So, remember that I said that I like to be called out on mistakes. That tells me you're paying attention. Okay, so this one here again, if you can't see the domain and range from the function itself, then sketch a diagram or a graph. So this is again the x-axis. This goes to the right 3. So let's say this is 3, and then this goes up 6, right? So let's say this is 6. So from here, the vertex is at 3, 6. So this is where the graph originates from. But notice that it has a negative in front of a radical, so that means this graph should be pointing down instead of up. So from this point, the graph looks something like this. It's not precise. This is just to give you a visual aid, and that will help you determine domain and range. So for domain, the farthest to the left this goes is 3. So then this is 3, and then it goes to infinity. So there we have domain of the graph. The range, this one has a top but has no bottom. So then you start always bottom to top. So on the bottom, it doesn't have one. It goes to negative infinity as it goes down. But then the highest it's going to go is 6. And this gets a bracket because it doesn't go any farther than that value for y. So once you have domain and range of f of x, then switch them to get the domain and range of its inverse. So then the domain of this one is negative infinity to positive 6, and the range is from 3 to positive infinity.